Thank you very much for the kind introduction. It's a great pleasure to be here. I think there's so much excitement about AI. It's fantastic to be here and actually talk about some of the stealth work that my group has been doing in Cambridge. And my talk today is about automating artificial intelligence. And here's my motivational gem. So data science is still very expensive. It requires human expertise still today. And we'd like to change that by automating everything. We'd like to automate data science. And really, it's sort of motivated by a very simple question, which is what sort of technology do we want to build? And how can we make machines most useful to humans? And really, it sort of comes down to three things, I think. One is the reliable automation of tasks that are usually done or carried out by humans, augmenting humans with powerful tools, and then thirdly, to solve tasks that go way beyond human capacity. So these are the sort of things that we'd really like to put technology to use for. And before I get into some of the sort of future tech that we're building in Cambridge, I'll talk a little bit about automation and where we are and how we got here. So first question is, why automate? Why automate anything? And the reason is maybe not so obvious, and my answer is we build machines because fundamentally we want guarantees. And the guarantees are about multiple things. For example, reliability, accuracy, precision, patience, persistence, speed. All these are qualities that we want to control, and we want guarantees over these qualities, maybe in a way that a human cannot give us such guarantees. So ultimately, that is a reason to automate. And one of the fundamental breakthroughs after the Industrial Revolution was essentially the invention of the computer. It is the notion that there is a machine that is most general and that can emulate the behavior of any other machine. So that was the first step that sort of took us here. And these machines are called Turing-complete or general-purpose computers. You all know this, of course, and you're all carrying Turing-complete devices in your pockets. And the input to such a general-purpose computer is a computer program, and the instructions specify precisely what the machine should do. And that's a picture of my hero. He invented kind of both computer science and, while he was at it, AI as well, so may as well. He was at King's College, Cambridge, and he sort of formalized that notion of a Turing-complete language, of a language that is powerful enough to capture all of computation. It's the most general category of language known, and that's not always a good thing, as it turns out. But this is sort of a very important class of languages to know about. Just a quick example. The theorists of you might recognize this. This is an extremely simple language that is Turing-complete. It fits on one slide, and it is as powerful, theoretically at least, as any computer is, and any computer program can be expressed in this language. Many languages that are in production are based on this, for example, Lisp and Scheme. There's an even more extreme form that doesn't even have any variables whatsoever. That's called combinatory logic. It turns out you can even make that stochastic. For example, you can define binomial or Bernoulli distributions just by sort of using function application. But we're not going to go there. The other cornerstone of modern AI is Bayes' theorem. You're all familiar with this probably, and it's the rule of inverse probability, of how to manipulate probability distributions in a way that is logically sound. So the question is, where are we today, and how does this form the backbone of today's AI? And I'll sort of say that the evolution of AI maybe went through several stages. The first one was the emergence of that general-purpose computer. And here, decisions by these AIs or computers are made exactly like the human devised a set of rules. So that rule set essentially determines exactly how decisions are made. Stage two, then, was the invention of ad hoc learning algorithms. That was humans figuring out, well, we want algorithms that go a little bit beyond that and do something slightly more general. And decisions sort of correspond to optimizing an unknown cost function. And these algorithms are typically not really clearly aware of what that cost function is necessarily, but in practice still very useful. Stage three takes us to Bayesian machine learning. And algorithms in that class essentially separate assumptions, data, and inference very cleanly. And what that means is that essentially human experts can engineer models and algorithms that sort of very carefully think about each of these components and separate these out, and decisions can be made near optimally given a specified cost function. Unfortunately, to do this exactly is usually impossible, and so we have approximations or approximate inference that we need to use. So the learning may have to go through some compromises. Then stage 4 is where we're headed, and that is automating everything, or sort of more stages of that process. And one of them is, instead of programming the model ourselves, let's just have the model be built by a computer as well. So this is automatic model construction. The other way to go is to say, let the human specify any model whatsoever, and that can be from a Turing-complete programming language, and let then have the machine figure out a way of applying Bayes' rule to it. How can the machine automatically figure that out? It's generally impossible. It hasn't stopped people from trying. It's a huge field of research called probabilistic programming. It's all the rage. It's fantastic. I wish I could talk more about it, but I'm actually going to focus on the second one. Just for completeness, I'll mention the third, which is to automate everything and to find a way of having a rich representation from a Turing-complete language to be the model that is being searched. That is generally known to be impossible, but that is the equivalence of solving and cracking strong AI. So, but now let's talk a little bit about seeing some of that in action, and in particular, automating the model construction, inference, and interpretation part. So really, we'd like to have an end-to-end system where we automate everything. So the user supplies some data, ideally, and the machine goes and does everything else. It constructs models, ideally more than one. It does inference, as in it trains the model, it learns, and it analyzes the results at the end. And given such a user-supplied data set, we really want the system to be autonomous in a way that is basic and principled, but also in a way that the system can explain to the user afterwards what it has done. So that is the basic motivation and idea behind the Automatic Statistician project in Cambridge. And here, it is really data-driven, automated model construction, and in addition to that, human understandable explanations that come out. Our prototype also has various other things that it does, for example, automated model criticism. So the objectives of such an automatic statistician, of such a piece of software, would be to either produce good predictions or to produce good explanations. And these two goals are not necessarily the same. They can be in conflict with each other. So it's important to choose what to optimize for. And so generally, an automatic statistician requires two things. One, a way to search and construct new models, and a way to compare different models given data. And then finally, to evaluate or explain these models as well. In the interesting cases, there are infinitely many models possible, and we're going to see an example of that in a second. And that leads to a potentially unbounded search, right? And you could imagine that you may want to have to prune that search tree somehow, and indeed, that's where a lot of the research lies. One key idea is to create a grammar over model constructions. So that grammar can then be used to construct models systematically, though not necessarily exhaustively. It's not necessarily interesting to generate all models. We want to do that search in a smart and intelligent way to generate only those that are really interesting. So here's a chart. I hope is that visible? OK. That roughly explains how such a system would work. So we have data coming into the system on one end. Then we have a search procedure that uses this language of models, that grammar that I mentioned to you, to construct new models and evaluate them. And then that evaluation informs what other models to construct. Then once a model is found, that model can be used to generate predictions or explanations, or it can be used for model checking as well. So our team in Cambridge has built a number of these prototypes, and some of it is based also on former members of the team. I have a demo that I'd like to show you in a few minutes. But first, let me show an extreme case where we have a grammar that you're all familiar with. This is a grammar over arithmetic expressions. So this is the sort of stuff you type into a calculator. This is an extreme case, right? So any number is composed of, say, a basic combination of arithmetic operations. And here's a system that you can use to invert and automatically learn such an expression. So I'm going to take a number and paste that into here. And I'm going to click search. And the automated engine will now go and try and find an explanation for that number. That number turns out to be square root of 3 plus 1. And that is indeed the number that I put in. You're welcome to try this yourself and give me a number by using your calculator. Just to note, this has a search depth that doesn't go all that deep for obvious computational reasons. But it uses a smart search that doesn't exhaustively enumerate all expressions. So as such, it is a basic first example of the kind of system that we may want to build. So how about other grammars? How about other things that we could possibly search and automate, other models that describe useful things? So here's a really, really nice one. This came out of work by Roger Gross, David Duveneau, Zubin Garamani, and James Lloyd from our lab in Cambridge. And here we have a Gaussian process, and we have basic kernels. You can think of these as properties of functions. And we have 5 basic ones of these, and they will form part of our grammar. And we have functions that are linear in trends. We want to model constant trends, white noise, periodic trends, and smoothly varying functions here with a squared exponential kernel. And here you can see examples of the sort of functions that can be generated from each of these base kernels. Then secondly, we have ways of combining these base kernels to make larger kernels. So for example, we have addition and multiplication to create various complex models that we can learn from data. So here the key thing is we take this grammar and we find a way of automatically searching this whole space of models to fit a sensible model to the data. So here's how that might work. Here's a tree over expressions, and you can see the function here in the corner. And we take those input data. In this case, this is a time series data set. And we're learning gradually with a greedy approach in this case from the basic grammar, which has the base kernels at the first step, and then basic combinations, for example, additions and multiplications at the second layer. And we evaluate these constructed models on the data and then see which ones are good and which ones are not. And ultimately, we end up with an expression that explains our data well. And because we were careful in how we chose those functions, they can be converted into human understandable reports at the end. I'll try and show you an example thereof. So here is an example of a report that was generated by the system. I'll zoom in a little bit. And the report contains various sections. It explains, for example, the components that make up the data that it found. And it provides graphs and explanations with the graphs that show what's in each component and how that contributes to the final model. So this is an example of a more complex automatic statistician. But it doesn't stop there. We actually have quite a range of different things like that. And we have the ability to show this more or less live, I hope. I don't know if there's enough time. Yeah? But as so often, demos can fail when you most want them to. I don't get my file open dialog. That's a shame. Well, I might try again at the end. So the future development of such technology is essentially going to see richer and richer grammars, including those that span multiple model families. And what we've built so far is a fairly generic architecture that allows us to swap in and out different components of such systems and use different grammars. And we've built a bunch of infrastructure around it as well that allows us to use this on a cloud, like this live demo. And we very much hope that this project can be useful, not just for research, but also for commercial applications. And that's kind of, I guess, where we're going. And the question is, can we automate all of data science? And there's a bunch of stuff that's really difficult. And the answer is, we don't know how to do it yet. And obviously, it's AI complete. The sky is the limit of what we can try to tackle. And we're very much still at the beginning with all of it. And as a final note, I think it's worth thinking about what we're optimizing for. As I hinted at in the beginning, it is very important to select the utility function that we want to optimize for. And one of them is explanation quality. So do we want to search models that lend themselves to good explanations for humans? Is that transparency important to us? Or do we just care about giving really, really good predictions, and we ultimately don't care at all about how the machine does it? If we have a black box approach, then that leads us maybe more towards neural networks, which is also a really fascinating technology. But it doesn't really help us make informed decisions as much. So this is why it is really important to choose what kind of model family is useful and important to us. And then also, there's always the computational bottleneck, I guess, and that has many consequences. For example, there's the accuracy trade-off, how accurate we want our outputs to be, but also how we can put our memory on our CPU cycles to best use given our utility. All of these are still fairly unexplored research areas where there's a lot of active development going on. So this was my brief talk on the Automatic Statistician project, and I hope you found it interesting. Please visit our website, and if you have any questions on any of these range of interesting technologies, please feel free to contact me and ask me. Thank you very much.